So first I would like to thank Microsoft for hosting this conference and for inviting me to speak. And I would like to thank all of you for coming. I hope that you enjoy my talk. And while I am sorry that I do not speak Korean, if you have any questions, please come find me. I can translate with my phone. Of course, I am happy to help if you have any questions. So the title of my talk is Pitfalls of Machine Learning, or otherwise, what you should learn from my mistakes. Unlike most of the other presenters here today, I do not work in machine learning. I work for a bank. I am not a technical person anymore. I am now a manager. It is a different way of viewing the world, says a man who was born in America, works in Australia, and is now talking to you in South Korea. So we can understand that we can all have different viewpoints of the world, and we can all learn from our differences rather than finding conflict. So myself personally, I have been educated in both technical and business. I have a doctorate degree in electrical engineering and a master's of business administration. There are not many people who can do both. There are people who do one, there are people who do others, there are people who focus on the differences, but I hope you will see that by bridging gaps and finding commonalities, we can solve many of the problems that I have had before. I've worked in a number of different industries for over 10 years. Banking, defense, and biomedical engineering. One of my proudest achievements is I worked on writing the first algorithms for the bionic eye of Australia. So I can honestly say that I have worked trying to bring sight to the blind. So I would like to share some of my experiences in industry and in machine learning projects. I found a few quotes from the internet that intelligence is learning from your mistakes, but wisdom is learning from the mistakes of others. So I hope that all of you are wise and can learn from my mistakes. There is also a slightly more playful quote that says, "Wise men learn from others' mistakes, and only fools learn from their own." So I want to cover different areas. I'm going to look at 3 different industries and 3 different topics. Now, these 3 industries are the 3 that I mentioned that I've worked in. But my 3 topics, I want to look at development, validation, and governance. Now, for many people, when they think about machine learning, they focus on the development. In my current job as a manager at ANZ Bank, I do the other 2. So while most people finish at development, that is where my job begins. If you learn nothing else from this talk, you should understand this, that my greatest mistake was assuming that all of the problems will be technical. In my experience, the opposite is true, and hence that is my current job. So let's talk about banking, and let's talk about developing machine learning models. So if I have an example, I want to value something. I want to look at how much a house might be worth. The reason I care about this is that if a person has a mortgage and they run into problems and they can no longer afford their mortgage, the bank may lose money relative to the value of the house and the value of the loan. In the terminology, this is known as loss given default, or will be abbreviated as simply LGD. It is one of the main components of credit risk, so if you go and Google credit risk, you may see references to LGD, but also PD, the probability that a customer will be unable to repay their mortgage, and EAD, the so-called exposure at default, which is, if they default, how much do they owe you? This was especially important during the global financial crisis, which hit the United States, and I will show why that is important soon. But I can have a simple model that my loss given default is how much is owed at default. Again, you may see that referred to as EAD, minus the house value. And so this house value is what I want to model in order to estimate how much loss a bank may incur in the event that someone cannot afford their mortgage. This is a graph of the median house price in the United States. The gray areas represent recessions. And you can see during the global financial crisis here, there was a severe decrease in house prices. And from a bank point of view, if there had been a loan written here toward the top, where house prices were high, of say 245,000 US dollars, and then a customer ran into trouble, house of their price went down, the bank may be liable for the difference, in this case 40,000. Note this cannot be negative. So if those values had been reversed, if in fact the loan was for 205,000, the customer could not afford their loan, the bank takes the house, the bank sells it for more than the customer owes, the bank does not keep the profit. So while it's important to model, the real question is, will the prices come down? So I've worked through an example using some open source data in R. And why I like this example is because there's a nice blog entry by this person. And the URL is there. You can Google it and find exactly what I've done. And I followed the process that the author suggests, so you can do all of this. And so you fit a neural network, and it looks something like this. I don't know what you're meant to do with this graph, but here it is. In particular, there is one number that I want to point out, just for reference. Which is 1.41. Now that doesn't mean anything by itself. But so I fit my neural network, I used it to predict house prices. Here I have the observed house price on the x-axis and the predicted house price on the y-axis. And if my model were perfect, they would line up exactly along the dotted line. And looking at it, it looks okay. There's no real pattern. If I make a graph of the size of the difference, or the residual, it looks normal. The peak is around 0. There's some other things on the outside, but largely this looks good. So you can say I have succeeded. I have made a model of house prices using a neural network. Good. Frequently in banking, we would use what's called a logistic model to estimate probabilities and to make other estimates relative for banking. Now, if you did not know what you were doing in a neural network, and you looked at it and you saw the word logistic somewhere, you may say, logistic is not machine learning. I don't want to use logistic. As it happens, the standard so-called activation function for a neural network is logistic. So if you saw that word and said, no, I don't want that word, I'm going to change this single item. I'm going to change the single setting because I do not want to use logistic, and you change it to hyperbolic tangent. Everything else here is the same. I'm using the same data, the same network coordination, and now that one number has changed. It should not surprise you that if I change the settings of my model changes. So now I want to look at it from the same way I looked at the other. Now there are two colors. There is the bluish green, as we had before, and now there is the brown color. You can see that they're similar. There are some places where the green is higher than the brown. There are some places where the brown is higher or lower than the green. So we can look at the plot, we can look at a histogram of the residuals, and everything looks slightly different, but at a high level the same. So what can I do? I can look at some metrics that says, well, what is the difference on average of the error? The lower the better. I can look at what's the largest error, the lower the better. And here I have a problem, because if I use the mean squared error, which one is the least wrong on average, I conclude that the hyperbolic tangent method is better. However, if I conclude that I want something that is the least wrong overall, then I conclude that the logistic is better. There is a saying that a man with one watch knows what time it is. A man with two watches that are different doesn't know what time it is. So here I am with my two models, both of which are comparable in performance. But now, when I want to actually predict house prices, which one should I use? Now, as the previous speaker was saying, I could say, well, I have two estimates. You can imagine a man with two watches who have close time. You take the average. You get an estimate here, an estimate here, and overall you estimate them in the middle. So that gives you the purple dots. And you can... So as a test, I can see that the purple dots are in fact in between the green and the tan. And I can say, right, this is my model. The previous speaker was talking about having more. You could have thousands of models. There are many, many, many settings you could change in your own neural network. Go crazy, change them all. But how many is that? Is that 100? 1,000? 1,000,000? Where do you stop? An expert on neural networks may look at this and say, okay, there must be some pattern here. There must be some reason why the tan one does better sometimes and the green one does better other times. This is a classification problem. I can train a neural network to tell me which neural network I should use. And if I could do that perfectly, then I would get the pink dots. And you can see a substantial reduction in my mean squared error. I can almost hear a consultant coming to me to tell me with their expertise, we could have a reduction in mean squared error of 33%. And I can imagine my managers getting very excited that they could get a 33% reduction in mean squared error if only they could predict which neural network would work better. However, the reason we are doing this is because we have said there is a difference in which neural network you use. And you can imagine that if you build a neural network to use which neural network, how do you configure that one? So I've got two neural networks here. I build a neural network to see which one I should use. That neural network has settings that I need to set somehow. And we know differences in the models will cause different results. So, I can build a neural network to determine which neural network I should use, to determine which neural network I should use. And you could keep going with this as long as you like. The histogram of the errors looks a lot better than before. But again, this presupposes that there is a way to perfectly decide which one would give the lower numbers. So let's talk about some of the pitfalls in this. The first one is machine learning even appropriate? I said that frequently people use logistic regression. Have you compared this to logistic regression? The previous speaker talked about ensembles and using hundreds, thousands. Have you tried using one? What do the errors look like? And if you take a step back, and again as a manager, that is the common thing to do, the goal here is to model house prices. I'm not trying to decide which neural network to use. So it's easy to focus on the problem. The problem is I want my metrics to be higher or lower. It's easy to focus on that and not say, well, is this actually helping me predict house prices? And even then, my problem is not predicting house prices. My problem is trying to estimate the losses that the bank will entail. So I'm 2 steps removed from the problem. And I'm starting to focus on that. That is a trap. That is a pitfall. When I'm talking about important metrics, I had 2 there, but you could think of others. What is the average percentage error? The maximum percentage error? What is the difference in loss? What is the difference in LGD? If you don't agree on what you're measuring, and if you're measuring multiple things, what do you do when one of them tells you one thing and the other one tells you another? You need to have these discussions before you go and implement your model. And of course, there are other ways to minimize these things. You could change your network configuration, or you could not use a neural network at all. You could use support vector machines, you could use random forest, you could use other aspects of machine learning that have nothing to do with neural networks, rather than getting stuck in how do I optimize my neural network. And again, this is just one term in the simplified version. And the data that I was using are median values. So even if I predicted it perfectly, there's still a 50% chance that the house price would be too high, and a 50% chance that for any given house, it would be too low. The next pitfall is frequently in these types of work. You will train your model with some training set, you'll finish it all up, and you'll evaluate it against your test set. My recommendation is to not do that. To first finish everything as if you had completely done the model, and then run your test. That means agreeing on how will your model be assessed. What metrics are you using? Agree that what you're doing is technically sound, rather than hitting the button, getting the results from your test, and looking at them. So your training results should be ready for validation. So to cover validation, I want to talk about my time in defense and use some of my lessons from defense and how they apply to validation. So some context. Many of you might not know what validation means. For me, this is where my job starts. So was the model development consistent with approved processes? The underlying assumption here is that there are approved processes. And you may have seen flowcharts of you source your data, you clean your data, you split it into training and test, you do some single factor. Could I reproduce all of that? Have you maintained the code to do all of that data cleaning? Or did you do it from the command line, or quickly in Excel, or something else that's not reproducible? And then secondly is the model fit for purpose. Now the Boston data that I showed you isn't fit for purpose because it's not a time series, but it is fit for purpose because I want to use an example with a neural network that's documented for all of you. The underlying assumption here is, do you know what the purpose is? Because for some cases, inappropriate data may be good enough for what you want it for. From a defense context, the first question is, well, is your data appropriate? Well, no, because I don't have a time series. The second one, which is a little bit harder, is how do you consider adversarial impacts? Now, adversarial means when I do something, you do something in response. So it could be simple like a game. Recently, AlphaGo beat a human for the first time in Go ever. So when the person makes a move, the computer makes a move, they're both doing so in response to what the other did, and in order to beat the other one, even if it's playful. So if I implement a model, the behavior of whatever I'm measuring may change. If you consider sensor data for tanks, I know that I can use the heat signature of a tank in order to find it. And here we have an image with two tanks. The bright one, and the second one that's camouflage, number 2 there. But I know that there's a means to camouflage tanks. So before, I was being kind of funny when I said I could build a neural network to decide which neural network to use. But suddenly, I might want to know if I'm looking for light tanks or dark tanks. And now we start to go around a loop, where the people building the camouflage know that I know they have camouflage, so they need to camouflage differently, and I know that they know to build different camouflage, so I need to find out what that is. And this is what's interesting about things that are adversarial, is they don't ever stop. I do something, you do something in response. I do something in response. In a game like Go, we can both see the board and we both have perfect knowledge. In defense, I don't know what the response even was. Or if they saw my move. Now this is on the internet, right? I know they're doing this. But other capabilities, what even are they? How do you know? So if I'm looking at adversarial impact within the space of image recognition, this is from a paper cited at the bottom, where on the left side we have some images, so the school bus down to the dog. In the middle we have the change that you do, and on the right side we have the final image. And neural networks have been built to classify all of these, and they do very well. So then we make the changes, and we have all of these images. And we run the neural network, which did so well before, and it misses all of them. In fact, it thinks that all of them are an ostrich. And so now we're in a case that we have a problem, because we have this neural network that takes inputs that we don't see the difference of, and yet it thinks it's an ostrich. Why? How? What happened? For traditional image processing techniques, you can look at features. You can overlap those features onto things. So for the dog, it may find the nose and the eyes. Or it may find, frizz around. For the school bus, it's looking for sharp angles. With traditional techniques, I can tell you why it thinks this is an ostrich. With neural networks, it's hard to know. If you want to take another case, if you think that machine learning can do anything, and you build your machine learning to recognize images, such as the ones on the left, the guitar and the penguin, you feed that into your neural network. Well, on the right-hand side, they have a genetic algorithm that says, right, I know there's a neural network on the other side classifying these images. I'm going to build images that will fool it. So if you say your machine learning can do anything, can your machine learning beat my machine learning? Again, in this case, the answer is known. So if I give a guitar to the neural network, the genetic algorithm sees that whether or not it gets it right or not. And I either give the neural network a true image, or I give it one that's come up by its opponent, the genetic algorithm. And I wait and see. And interestingly, if you look at the probabilities at the bottom, the confidence that the guitar is actually a guitar is less than the confidence of the wavy lines being a guitar. So in an adversarial sense, my machine learning has beaten the machine learning. And again, you can go around this as long as you like, but the neural network learns that, okay, it was tricked. That was actually a bunch of wavy lines. That wasn't a guitar. The neural network improves itself. The genetic algorithm then says, okay, I know the neural network knows this isn't a guitar. I need to change it. And you can keep playing this for as long as you like. And you may say, well, I don't work in defense. I don't need to worry about this. So from my learnings, I know that website analytics are used. That behind some websites, there's a machine learning algorithm that's tracking me. So I want to look like someone who is interested in a product, but is price sensitive. So I go, I log on, I add items to my cart, I check shipping costs. Shipping to Australia is normally expensive. I sit on it for a while, I read the reviews, I delete it from my cart and log off. And I wait. Sometimes after a week, I get a nice email saying, hey, you're interested in this, aren't you? How about taking 20% off? Here's a code. Thank you. I'll take that. My adversarial neural network has tricked the machine. You can also do this if you use Google Chrome. There's the setting to go incognito, where it doesn't use your cookies or your data, or just log in from another computer. And sometimes you'll get a different price. Pick the smaller one. You can also turn chatbots into trolls. This is a rather famous example where Baron Binghamton here asks the chatbot, do you support genocide? And the chatbot responds with, why, yes. Yes, I do. Now, it's unclear if there was anything before that. If I want to trick the chatbot, I first send the chatbot a tweet that says, hey, I really like genocide. Genocide, that's great stuff. I'm priming you up. And then I delete my tweet. And then I tweet this. Let's be clear, there's no reason to ask this question. I've never gone to a party and met someone for the first time and say, hi, nice to meet you. Do you support genocide? The only reason to ask this question is to be adversarial. But trolls will do this for you. So you implement your machine learning, you set it loose to the world, and there are some people out there that just want to cause problems, even though there's no real advantage to them. So along those lines, some other people have tweeted to say, look, this happens. Teach the chatbot that this is wrong, but let it keep running. It needs to learn for itself. How to respond to someone who asks such silly questions. Even then, it's not an easy answer. What do you do with someone who is rude? Do you ignore them? Do you insult them? Do you answer them honestly? What is the right answer to this? So, looking at validation and some pitfalls, the first one is that machine learning occurs after data science. In my opinion, the title here should be reversed. It should be data science and machine learning. So if you are looking at your data, and it may be very clean data, it might have no outliers, no missing values, but in the future, if you do get them, what happens? If you look at Google cars, right, they drive themselves. There's great machine learning that teaches you how to drive. The machine learning gets all this attention, and everyone thinks of them being autonomous and everything else. And there's some great technology behind that. But if there's a competition, you can have all of that. You can have all the machine learning. You have all of their code. And I'll give that to you, and we'll have a competition. I get their sensors. So now we'd be in a case where I have all this data, and I need to figure out what to do with it. And you have this beautiful machine learning that takes input data that don't exist anymore. I'll take that trade anytime. The other lesson is that if you start changing the incentives, people behave differently. I've heard this explained as the one-sentence definition of economics. So if you're going to implement something, you need to be ready for the fact that whatever you're measuring, whatever you're doing, may change in response. And again, I haven't run my test data yet. I'm still looking at my training data. And that should be ready for governance, which I want to consider from the context of biomedical engineering. So what do I mean by governance in a biomedical context? So first, governance. Let's say I've done my development. It's gone through validation. We're ready to go. We know what we're measuring. We know that it's good. We know it's good for purpose. We have ways to deal with messy data in the future. Now I want this to go live. How do I do that? So in the case of the bionic eye, that meant I'd written all the software, we had tested it in the lab, and now the time comes to surgically implant an electronic device in a blind person's eye. I can't do that. How do I do that? Who needs to give approval? Obviously the person whose eye I'm going to plant it into. But so from this biomedical context, in Australia there's a regulatory body called the Therapeutic Goods Administration, and they get to say yes or no. So even after I talked to my managers, even after the CEO himself could have signed off about this, we're not yet ready to actually implant something into a human being. And there's also ethical questions. Is it right to do this? So if we look at this idea of getting regulatory approval, there are standards. There's a standard called IEC 62304, which covers software for medical devices. So this is an excerpt, which you can download online. But in particular, there's this graph on the right, which includes the processes for development, validation, and governance. And if you're working in machine learning, you're probably used to the development. I've just talked about the validation, but now let's talk about the governance. If you've done the development and validation, according to standards, you should have had a development plan. How are you going to develop this? What are the requirements? Have you designed your software at a high level and detailed, and tested it at the unit level, the integration level, and the system level? You should have means to handle software configuration and risk management, so source code, Git, code repositories, so that when we make changes, we can say, yes, this is the version of the code that passed testing. And a means to resolve problems. So then we start to get into this ethical part. There's a blind person in front of you. You've been speaking to her. You know her about her family. You've done all of this. The only way to know if she will see things when you turn it on is to do it. Is this the right thing to do? Are you comfortable? So we did that. We turned it on and she said, yes, I see. We hit the button and she sees a flash of light. If you read her interviews, she said one of the best feelings that she had was all the joy that we felt because we turned it on, we sent in some current, and she said, I see. It was just a flash of light, right? It's not like seeing all of you here. So then that worked. She can see flashes of light. But now we need to give her more information. We want her to be able to see faces. We want her to be able to not run into things that are sitting out on the floor. We want her to not drop off the edge of the stage. This means turning on multiple electrodes. We've never done this before. We make changes to the code. We test it. The only way to know what a person sees when you activate multiple electrodes at the same time, do it and ask them. In some ways, it is easier to do this with a person than with an animal. Because with a person, I can have a relationship with that person. She can say, Craig, I trust you. Tell me what you've done. Tell me you're comfortable. Okay. And I can turn it on and ask them. If I were to implant this in an animal, I can't ask them if it's okay. And when I turn on the device and start acting multiple electrodes, I can't ask them what they see. So it doesn't actually answer my question. And this all may seem like it's a lot, and it's so much information and so many steps, but it is considered best practice. And again, as a manager, if I take a step back, if I'm going to do something to another person, I should be doing the best possible job. With the development of Agile software, perhaps this will change. If Agile software becomes provably better than this kind of standard process of defining your requirements, doing your architecture and detailed design, then this should change. Because clearly, whatever you do with a person should be the best you can do. So you do all of that. You build things to the highest standard. You get your model validated. You establish a governance process. And still things can go wrong. In biology, this may mean that people die. There was a case not too long ago of a pharmaceutical company that developed a new drug, went through all the tests for their new drug, got some volunteers, and someone died. There's some natural questions arising from this. First is, what did we do wrong? It is sometimes a false choice. It is natural to think if I have two options, that one of them is right and the other one's wrong. It's possible they're both wrong. It's possible they're both right. It's possible that the question is wrong, and this person that you think is very sick, in fact, isn't, and you're treating the wrong disease. Could we have done better? All of these standards and all of this governance exists to make the answer to this no. That we did our best. People are sitting together defining what the best is, and we did it. I was careful to say we in both of these questions, because note that this is not a one-person job. Because the regulatory authorities recognize that people make mistakes. I don't care how smart you are. I don't care how good you are. People make mistakes. It is never the fault of any one person when something goes wrong in industry, because there should be people validating your work. There should be governance set up around your work. You should have gates for how high things can be and still be acceptable, or how low. It should never be the fault of any one person. That said, you may ask yourself, what if I had what? You may ask yourself this in any personal or professional sense. In my experience, this was the greatest pitfall I've ever had. If you look at AlphaGo, it played itself millions and millions and millions of times. That means it lost millions and millions and millions of times. But the point isn't, did you win or lose? The point isn't, did it work or not? The point is, did you learn? Even when the stakes are at their absolute highest. If you learn, you know what not to do in the future. You know to investigate what had happened and learn from it. And frequently some of the greatest advances come due to understanding mistakes. And as I get older and move into management, I care a lot less about house prices, mean squared errors, maximum absolute errors. And it is questions like these that occupy more of my time. And if machine learning really is all the greatness that it is, let's not worry about chatbots. Let's not worry about finding tanks. Let's go cure cancer. And even though machine learning can do all of those things, it can't answer these. What should we be solving? Why are we solving the problems that we are? What is truly important to you? And what are you doing about it? And those questions, as you may have noticed, aren't technical. So if I go back and review kind of the pitfalls in development, first off, is your solution appropriate? Should you be doing machine learning? Are you solving the right problem? Have you asked the right questions? Make sure you focus on the goal, not the algorithm. It is easy after you've spent months or years developing something to really love it and to think it can do everything. But if it's not answering your question, leave it. For validation, no matter how good your algorithm is, if you don't have good data behind it, it probably won't work. Or it won't work as well as it could. And that if you start measuring something, you may change it. You can see this in terms of the way I behave with websites. And you can also see, I taught for a while, and you can see with students that once you say this is what it takes to get an A, to get the highest mark, you need to get here. There's suddenly a lot of students right here. Somehow they manage to go from here to there. There's very few. From a governance point of view, you should always wonder, can you do this? Is it legal? Is it ethical? Again, that's not a technical can you do this. Machine learning, you can throw data at it and it will come up with solutions. But is it right? And finally, the can you do this is if it fails, are you prepared? Thank you.
네, 지금까지 멤버 시리즈인 데이터 사이언스 커뮤니티에서 오신 크레이그 세비지의 발표였습니다. 여러분 다시 한번 감사의 말씀을 드립니다.